Okay, good morning. This is the first idea of the section 1.5 parent functions. I'm going to use this projection to help with the simple ideas of parent functions and their transformations. Now, we've seen transformations on functions before, and we probably didn't know what to call it in the past. But I'm going to talk about first what a parent function is. The parent function is the function in its simplest form, be it a straight line that crosses through the origin and has only a slope of 1. So f of x equals x. We have that straight line, and I'm going to show you what these look like momentarily. I just wanted you to see that a parent function is that same type of function. It's got the same look to it, be it a parabola or this type of parabola. This is a punt, or some sort of straight line, or what have you. And now I'm just going to go through the list. And once I'm done with the list, I'm going to close this out and move on to the next piece of the puzzle, which is looking at how these things transform and trying to link it to ideas that you already know. So here's the first part. I'm just going to pull this down so I can see the first 4 types of parent functions. All right. The first one is a constant function, and that's x equals some number, right? And that's our graph, here, but that's not really a function because that's infinitely up and down. So a zero function is f of x equals some number, all right? And that's a horizontal line that just crosses through that number. So this particular function is f of x equals, it looks like 3.5. So I'm going to say it's f of x equals 3.5. And you can see right here at 3.5, it's just a horizontal line. And you've seen that before. I don't know if you've talked about it before, but the parent function of this is just a horizontal line wherever that y value is along the y-axis and back and forth horizontally across. The next one you've seen, millions and millions and millions of times. It's that identity function. We call it an identity function. The first one was a constant function. The second one is an identity function. This is our simple linear function, right? It's just a straight line, and in its base form, it's just f of x equals x, or y equals x. And then it crosses through the origin here, you can see it, and then it just has a slope of 1, right? So it's just up 1 over 1 and constant all the way through, back and forth. The third one we've been talking about a lot this year. We've been talking a lot about the parabola, right? And it's called a quadratic function. And I've tried to use the language, and you too should try and use the language. A quadratic function, and its parent function is just f of x equals x squared, okay? And so it just has that square term in the front. And the parent form of it is a parabola whose right there, that minimum right there, its vertex right here, the minimum hits right there at the origin, and if we talked about it, it's a reflection upon itself, right? So even if we put values in here for f of x equals x squared, we put it in an x, we put it in a y, or an f of x right there. We could say that 2, and then we'd say -1, 0, and 1, and then we'd say, if we put in a -1 and square it, we get out a 1. Put it in a 0, we get a 0. We put it in a 1, we get a 1. And what, you know, if we put in the 2 and the negative 2, we get out 4. And so we could plot those points on the graph itself. And I only did that one. So these are the 4 points I created, and this is going to be a reflection of itself if I put the negative 2 in here. And we have this nice parabola. So the idea of the parabola is pretty familiar to you guys. And so the parent function is the one that has a vertex right there at 0. And its function is f of x equals x squared. And I'm going to move on to the last one that we look at for our purposes that looks like a function, doesn't look any funky, no funky business, no asymptotes, no nothing. It's that cubic function. And we learned that if we cube it, we are pointing, it's odd, so it points in 2 different directions, right? And it just takes a turn. It would have been a parabola, right? This is just the opposite, but if we flip this up over the x-axis, we would just have our parabola. But since it's cubed and we deal with negative numbers, we understand that it works. And I want you to think about this idea, because when we start to transform, I want you to start using a little table, okay? A little input-output table or an XY table. So I'm going to create an XY table for this, or an X and f of x table here. And I'm just going to put in those same values. I'm going to put in negative 1, I'm going to put in 0, and then I'm going to put in the number 1. And so as we slide across this graph, we look, we put in a negative 1 and we cube it, we get out negative 1, because negative 1 times negative 1 times negative 1 gives me negative 1. And there it is on the graph, and we can put a point on the graph. All right, get used to this idea. You put in a 0, cube it, you still get 0. And then last but certainly not least, we put in positive 1 and we get out a 1. And then we get that turn, right? It's nice to know what happens if we put in, let's say, negative 2. Let's see what happens when we slide out here to negative 2. We do get a value out. It does exist, so we don't have an asymptote. And negative 2 cubed is negative 8. So negative 8 would be probably right about down here, 2 negative 8, and it would just continue to go that way. And that's what our function would look like. It's nice to know that 2 cubed is negative 8. That way when you're creating your transformation later on, you can shift it over and know that it's just, you know, you count up another 7 spots or down another 7 spots from your 1 away when you're creating this. That way you know that the function doesn't shoot out way over to the left or shoot out way over to the right, or out way positive, sorry, to the right or to the left. But that's the idea. So those are those functions. Get used to putting a little table next to it so you can understand and recreate those functions. And then I'm going to show you 2 more, and then we're going to move on. Actually, I think I'm going to show you 4 more. All right. So the square root function. The square root function is kind of cool because it's f of x equals the square root of x. Well, the cool thing about it is there's no negative part to it, right? It only exists with positive numbers. So for me, I like to use those numbers that are actual square roots. So I'm going to use 0. I'm going to use 0, 1, and 2. That's going to give me that parent function. It does, of course, begin at the origin. Doesn't go anywhere else after that. So it doesn't have an arrow on the other side. It only starts right here because we can't have a negative square root. This would be if we could, we'd have a parabola going direction. But it doesn't, it can't be a function that way because it would, wouldn't pass the vertical line test. But this is what that function looks like. And if we put in a 1 and take the square root of 1, we get out a 1. I lied to you, I don't like 2. I'm going to use 4, right, because that's the next perfect square. And then if I put in a 4, I get out a 2 because the square root of 4 is 2. And I can graph those points 0, 0, 1, 1, and then 4, 2. And now I understand my parent function that's a square root function. Other than that, not a big deal. Just make sure that your square root function doesn't go shooting way up in the air. It's going to basically bottom out, just keep going. It does come up. We obviously know that it comes up, but it doesn't go all that high, all that fast. But eventually it does. Last but certainly not least, on this page, I'm going to turn the page and do 2 more. Last but certainly not least on this page is the reciprocal function. And the reciprocal function is just simply f of x equals 1 over x. And we know that that's going to have an asymptote. And what I want you to think about when you're remembering what these functions are, and I'm going to be going over it again in class, or you can watch this video again, or when I do the problems, I'm going to try and remind you of what these actually look like as parent functions in their simplest form, right? Before we start to do the work, because that's always going to be helpful. If we can remember what this looks like, we can see what sort of transformation has happened to it, or if it's shifted one way or another. Okay, so this has the 2 asymptotes. It has an asymptote here at 0, and it has another asymptote here at 0. And what that means is it never actually reaches 0. If x is 0, it doesn't exist, right? And there's a little bit here. You'll never get a 0 out is what it says. You'll never get a 0 out, and because there's always a 1 there, you'll never get to 0 over a number. It's just because there's a 1 there. And that's it. There's a 1 in the numerator, therefore you can't reach 0. You're going to get infinitely close, right? Because 1 over, 7 billion is one tiny piece, it's so infinitely small, but it does exist. And, in science, we can virtually detect things that are in the billions, and it does exist. So we need to know that it never really gets to 0, only because we have that numerator of 1. Spoken too much about it, apparently. But we know that in this situation, x can never be 0. And, if we want to know what types of values, if we need to know where to graph this, we know that if we create our input-output table and we put in -1, we will get out -1, and that makes perfect sense. 1 over -1 is -1, and 0 does not exist, so we have an asymptote right here at 0. That's what that means. And then if we put in the +1, obviously 1 over 1 is simply 1. And then if we wanted to put in other values, we wanted to put in a half, we would come out with 2. If we wanted to put in 2, we'd come out with a half. We could do that pretty simply. You guys are pretty smart about that. But I want you to see that here's this, and we know that it's just going to be this little curve that never really gets to 1, comes through this point and again comes infinitely close but never touches. So it's going to be a little bit easier on your paper when you draw it than me trying to draw it on this board, but that's what it looks like. The last things I want to show you are on the next page, so I'm going to turn the page here, and remember that's the reciprocal function. And we all understand what a reciprocal is, right? It's just that value turned upside down on its head. All right, so we have two more. The first one you've seen before, this absolute value function. You've seen this a million times, hopefully a million times. It's just that V formation, right? It would be a linear function. If there were no absolute value symbol here, it would be f of x equals x. And we'd have that linear function that went from here to here, right? But this is an absolute value function, so we have f of x equals the absolute value of x. Therefore, when we put in a negative number, the absolute value of that is always going to come out positive. So we could do, let's use a regular table, x and f of x, and we'll still, I'm going to use -2. This is just sort of an extra one that I'm putting on there. The absolute value of that is 2. -1 is where I usually start. This is just extra that I put there. -1, 1, 0, 0, and +1, 1, because the absolute value of -1 is +1. But I put in the -2 because I want you to see that +2 comes out. And then -1, 1, and 0, 0. And the good thing about it is you can just create these perfect straight lines. And I know I didn't draw it perfectly right there, but that's the idea. So we know that the parent function sits here, has a vertex at 0, and makes a V in a simple linear shape. It just has a slope of 1. So that's slope of -1 on this side, slope of +1 on that side. It's very easy to draw. So if there's any sort of transformation, which I'll get to in the next video, I'll get to that video probably in a few minutes, but I want you to understand these parent functions first. The last parent function is a function that you probably don't know the name of, but you've seen before. It's just that simple step function. And I want you to see it's called the greatest integer function. And all that means is what's the greatest integer next to a certain number, right? It's got this weird double bracket. You can go ahead and just bracket it when you're doing your homework. The easiest thing to know about this is that when we're talking about the greatest integer, it's the greatest integer that's less than or equal to the value that you've been given of x, right? The greatest integer that is less than or equal to x. And I need you to understand that. Why? Because if there's a function, let's say the function of x is that funky bracket, and you can just use regular brackets, you don't have to do this like I'm doing here. We're looking for the greatest integer that is just less than that value. So if I put in, let's use what they're giving you here. If I put in -4, we can go ahead and go right at -4, and that's part of it. But what if I said -3.2? So if I'm looking at -3.2, right? Well, -3.2 is just about here. And what is the greatest integer that's less than -3.2? Well, we'd have to go back to -4. See how it exists right here? Right? We started here and we look down the graph. There it is. And it's a perfect, look at this perfect step function. And I want you to notice two things. I want you to notice that it includes that integer to the left. But it doesn't include its open circle here at -3, right? -4 it includes, but it doesn't include -3. Why? Because if you were given -3, you'd be stepping up here to this part of the graph here and given -2. All right, so it exists up here, therefore it's empty right here. But everything getting close to it, you know, if I'm looking at like I said, -3.2, yeah, the closest integer would be -3, but the closest integer less than that value that I've been given obviously was -4. If you have any questions about that, go ahead and shoot me a message. I'm good to go. Trying to explain that little problem there. Those are the 8 types of parent functions that we're going to be talking about, and we're going to be transforming in this section of the book. I'll get back with you and we'll start talking about what those transformations look like and how to go ahead and draw them. We're going to use just simple mapping skills, putting it on the coordinate grid and mapping that parent function idea, and then shifting it over if we have something added or subtracted outside, and if it's added or subtracted inside, we're shifting it up and down. Whatever, that's the inside shifts it right to the left, and outside shifts it up and down, and we'll go over how those transformations occur in the next video.